My name is Fred, and I'm a data addict. Feel free to ask questions throughout the presentation. So I'm a developer evangelist at Circonus, which means I'm an engineer who goes around and talks to people. I've been a recovering C and Perl programmer for a while, though I've started to write C code again, and I really love it. I've been using histograms for operational time series monitoring for about 7 years, but I've really been geeking out on histograms for the past couple years. So at Circonus, we do large-scale, very high-volume time series operational telemetry, and the development of our systems has been driven through pain. When Circonus started about 8 years ago, the people doing it, the founders, set out to solve problems with distributed systems, and so they used observability tools like dtrace. And what they got was just a fire hose of telemetry from that. So they tried hooking up, monitoring systems like Nagios. I'm not sure if Zabbix was around that time to it, and basically those systems just fell over. And a lot of those systems also were using averages as metrics, and as they found that that gives you one data point, but for doing statistical analysis and advanced computations, it's really kind of useless. So they set out to start to use histograms to solve this problem. So who here is familiar with histograms? Raise your hand if you've used one. Wow, that's pretty good, about 75%. So I'll just go through some of the basics. This is a histogram. It's a skewed histogram because the mode is on the far left. You can see, the median is around the middle. It's to the left of the mean because the histogram values are skewed to the left. The 90th percentile, also known as the 0.9 quantile, is off there to the right. 90% of the values are below that. And the maximum value in quantile notation is Q1 at the far right. The Q notation for quantile notation is just a fancy way of representing percentiles. So this is a heat map, and this is basically a series of histograms over time. Each vertical slice is one histogram of data. This altogether is about 6 million data points. And the red portion of the heat map represents a large sample density. So this is actually load balancer request latency. And as you can see, you've got grouping there in the middle where it's red, the scale's at the bottom. And so you can see a lot of the requests kind of group around the 500 nanosecond threshold. And originally when I saw this, I was like, wow, this looks like the display from Knight Rider in that TV series movies with David Hasselhoff. But no, this actually contains a wealth of useful information. So I'm going to go over a few histogram types. There's fixed bucket, approximate histograms, linear, log linear, cumulative, and then we've got a bonus one too. So fixed bucket histograms are histograms where you specify the bin boundaries manually. The terms bucket and bin are kind of interchangeable. Bucket's more of an industry term, but if you look at some of the academic literature, they use the terminology bin. So this has some traits as it, if you're using something like this to collect data, odds are you're not going to get an optimal, you're not going to find the optimal bin boundaries. There are some mathematical theorems you can use to do that, like Sturge's theorem. That's a bit out of the scope of this talk. It's a little bit difficult to merge different histograms together that have fixed buckets because often you're not going to get a standardized bin boundary. I keep saying bucket when I should be saying bin. But these are commonly used in time series telemetry. The Prometheus monitoring system uses these. Approximate histograms. So this is an example of an approximate histogram was developed by Ted Dunning, and it was called a T-digest. And basically the way it works is you have a set of centroids here, and on each centroid, the distribution of samples surrounding that centroid are equal. So you've got an equal number of samples represented on either side of the centroids. And so these kind of represent groupings of data that would correspond to the bars on the histogram. These tend to be very memory efficient structures and have high accuracy at extreme percentiles. But at median percentiles, they do have some non-trivial errors around 10% with small sample sizes. Did we have a question? Okay. In terms of other traits, they are very mergeable, easy to merge with other histograms. Linear histograms. Pardon me? Linear histograms. So these are histograms that have evenly spaced bins. So you could have if you have a range of values, 0.1 to 10,000, you could have bins every 0.1. Now, going up to 10,000. Now, obviously, that's a tremendous number of bin sizes. So you do suffer from some excessive memory usage if you implement this in a production system. You do get some low accuracy at your lower values, but there's also a trade-off there. Like as you go with higher values, you get higher accuracy because the bins become a fraction of your data set size. But generally, this is not really, this histogram type doesn't have a lot of pluses. So, log linear histograms. This one's my bread and butter. This is what Circonus uses. So these are histograms with logarithmically increasing bin sizes. So you'll have 0.1 to 1, 1 to 10, 10 to 100, 100 to 1,000. And so these allow you to capture a wide range of data points without really having to know up front, like, what does my data set look like? Do I have data from 1 million to 10 million? Do I have data from 0.1 to 5? These kind of fit all data sets very well. You can have worst case errors of, I think, 5% if you have one sample that's on the very edge of a bucket. Say, like if you have a sample of 109.9, that gets grouped into the 100 to 110 bucket and gets represented as 105. But we don't really use histograms to store single values. We want to store thousands, tens of thousands, or millions of values in these histograms to examine the data. HDR histograms, high dynamic range histograms, are another type of log linear histogram that you'll see in industry. And we're going to dive into this in depth in a little bit. Cumulative histograms. These ones are pretty interesting. So the way that a cumulative histogram works is each successive bin moving right contains the number of samples of the bins on the left. So they kind of stack together. And the bin on the far right is going to contain the total sample count of all the samples in the histogram. You may have seen this if you've ever looked at photography color gradients. You'll see kind of like a black and white threshold curve. That's a cumulative histogram. It's sometimes known as a cumulative distribution function. This does have some significant advantages in that it's very easy, or it's easier to calculate quantiles. If I want my Q1, my 100% maximum, that's just the count on the end. If I've got an even number of buckets and I want to know my median value, I just go to the middle bucket and look at the count there. So this has some advantages in telemetry monitoring systems. Google uses this type of histogram for their Monarch monitoring system. So they're using it at a fairly decent scale. And when I was putting this presentation together, when I was researching histograms, I made a mistake. And I thought, oh, well, a cumulative histogram, I read the description wrong. I'm like, well, that just adds up values over time. And I was totally wrong. But what I realized was, you can take the traits of any of these histograms and put them together to create a custom histogram if you've got a well-known data set or if you just want to try something new. So let me go back to the cumulative histogram. If this indeed does represent increasing values over time, so I could have a very flat histogram at time equals 0, and I could have something like this at time equals 100. Well, then I could, if I wanted to calculate my 99th percentile for that whole time range, I've got essentially an O1 operation constant space and time operation to do that calculation, because I don't have to go through T1, T2, all the way to T99 and subtract each of these histograms. So you can kind of, if you find you've got a unique data set and something that you might be able, that some of these other histograms don't fit well, you can go ahead and roll your own. It's not that difficult. So I'm going to start diving into the open source histogram implementation that we've done, the log linear implementation. If you guys have your laptops out, I'm sure folks do, you can follow along. These are, we have a C library and we have a Golang library. So if you want to pull these up, you can take a look through the code and search for, I think it's approx quantile function, because I'm going to be going through how do we take a log linear histogram implementation and compute quantiles, and later on compute inverse quantiles and do really fun things with them. And we'll be addressing why does this histogram style scale and why is it fast? So this is a visual representation of one of our log linear histograms. If you look at, it's about 100,000 through a million in terms of sample values. You'll see the buckets are very finely divided, and then at 1 million, the bucket size increases. This next slide shows it a bit better. So we subdivide each power of 10 bin size into 90 bins. And originally, when I started looking at this in depth, I was like, well, why isn't it 100? I'm like, oh, well, it's 10 minus 1 is 9. And so if you divide that evenly, you've got 90. So that was a little misleading to me at first. But at each logarithmic exponential change, we increase the bin size by 10x. And so this, this gives us a lot of accuracy while still giving us a very high dynamic range, depending on our sample set. This is a different representation, just a different visualization of the same log linear histogram. The bucket transition is a little bit clearer here. It occurs, looks like around 1,000, or increase the bucket size. So how do you put something like this into code? The way that we do it is this is our bin data structure in both the C and Go code. It's got 3 components. We've got the value. So say if I wanted to represent 1.6, I would represent that as an 8-bit integer, but I would multiply it by 10. So really my value is value times 10. And then if I'm say I'm doing 1.6, my exponent is going to be 0. So 1.6 times 10 to the 0 is 1.6. So I've essentially allocated 2 bytes here for specifying a value and an exponent. The exponent does have a range of negative 128 to 127. So we can take very fractional, very precise fractional values represented in this histogram. And then we have also the count. The count's represented as an unsigned 64-bit integer. So we get a maximum of 8 bytes there. So as you know, we can store essentially an unlimited count in there for all intents and purposes. It is a maximum of 8 bytes that it takes, but we have applied variable bit encoding so that in some cases we can represent a histogram bin in less than, or represent the count in less than 8 bytes, and so we'd get the whole structure in less than 10 bytes. So that's fairly memory efficient. It's not 100% optimized, but it was good enough that we could really scale our system pretty far. So if you were to just have a similar data structure, like an 8-byte or 64-bit integer to record average values, you can do the same thing. That's pretty efficient, but obviously you're only getting one value if you're just using 8 bits to store, or 8 bits to store 8 bytes to store an integer. But with a histogram data structure like this, you can store essentially an unlimited amount of samples within a very narrow range. So what kind of efficiency do we get with a structure like this? Worst case scenario, I'd put out the calculations here. So one question there is like, how, if I showed you this histogram back here, how many bins do we have? Practically speaking, we found that all of our data sets, we've never gotten any more than 300 bins used to represent the whole range of data. And at 10 bytes a bin, and all the other conversion factors, you're looking at about 124 megs to store 30 days of 1 minute histograms. That's quite a bit of operational data. I can store, latency from 1,000 servers aggregated over 30 days in 124 megs, and that's also sub-second disk read, so it's very performant. Additionally, the bins are not pre-allocated when we store them. So if I have a range of 0.1 to a million, I'm not going to allocate every single bin up front and then leave empty bins. We only allocate memory as needed. So that allows us to really get an efficient footprint here. Now, if I were to compare this to, say, 30 days of 1 minute average data, that takes about a third of a megabyte. But once again, that's you've got 30 days of average data points. That's not very useful. You can't do much with that. Similarly, for a year, the footprint is not that big. We can merge histograms together. I mentioned before, like if you lined up the bin boundaries, you can easily merge histograms together programmatically. So we can take that 1 minute data we had in the previous slide here. We can merge it into 5 minute histograms, and we can get 5 minute data distribution resolution for a year, and that takes up about 300 megs. So again, on most modern systems, that's sub-second read. And if you'll notice, the total number of samples is somewhat invariant to the total data set size. The biggest factors are in how much data is stored are the span of bins that you're covering. Once again, we found 300 to be about the maximum, and also the compression factor for bin. We're using variable bit encoding, so that can change. So I showed before, we can have 90th percentiles, we can have medians, we can have 99th percentiles. How do we calculate those from the histogram data structures that we've shown? So if we use the quantile notation Q of x, where x ranges from 0 to 1, 1 being the maximum, the calculations are actually not that difficult. What you want to do is essentially sum up a count of every single bin. And if you recall the cumulative histogram, the far right bin holds the maximum value. You've got an O1 operation there now instead of an ON operation for most of the other histograms. So you can get, I think that may be why Google's using it with Monarch. You can get a little bit of optimization there. And then once you have that count, if I want the median, the 50th percentile, I would multiply 0.5 times that count to get what I'm calling Q. Q is basically that count in the histogram where I want to find the corresponding value. So once I've got that, say we have Q or X is 0.5, C is 1,000. We're going to get Q equals 500. We want to walk the bins, sum the boundary counts of each bin until we hit the bin where 500 is in the middle of the right boundary count and the left boundary count. And from there, we can use linear interpolation to calculate what my value is for that quantile. Now this might be a bit heavy without writing this down, but I'll be happy to go into this in depth at office hours. But linear interpolation, say we're looking for Q I'm sorry, we're taking the 50th percentile, and Q turns out to be 700. We can use this formula here. I don't know how many folks remember, well, it was middle school when I took it, algebra. I dove into this, and this is directly from the code, if you guys are following along in the code. We basically take the left value of the bin, which is 1.0, add that to 700 minus the count of samples at the left bin boundary, and we divide that by the right bin boundary count minus the left bin boundary count times the bin width, which is 0.1, and that gives us our answer of 1.05. So quantile calculations here are not mysterious. They're not as difficult as they may seem, and it's pretty straightforward to implement. And I want to emphasize once again, cumulative histogram really does have an advantage over here, because you don't have to do that initial operation of walking each bin and getting a sum of the count. So I'm going to do a quick recap here. We looked at several different types of histograms and how you can do your own. Showed the data structure and how it's space efficient. But the title of this talk is managing effective management of high volume data. So you can kind of see that we have a space efficient structure, and that gives us some scalability. But how do we make it fast? In terms of programmatic approaches, there are certain things that you should do and that we do. You want to avoid allocating memory unless necessary. If you look at the C implementation that I showed earlier, it does as much. It goes through a lot of work to avoid any spurious memory allocations. We do have to allocate memory when we create a new bin. You want to avoid copying data. You want to do pointer arithmetic anywhere you can. You want to avoid weights, and you want to avoid locks. So we do use a fair amount of assembly code to accomplish that. Concurrency Kit is a library that we've used to implement our histogram libraries to make them fast. That's built with a lot of assembly code in there. I'm not recommending that you go out and start writing assembly code. A lot of people have already done that for you. But what other things can we do with large volumes of data once we've gotten into a structure like this? So the stuff that Circonus is focused on, and where we felt the pain in trying to develop these techniques, has been operational data. So say, I'm sure everyone heard about the Spectre patch recently, where you could use, the CPU would preemptively calculate possible branch paths for code, and that turned out to be a security hole, because you could figure out what might happen before it would happen. And a patch came out for that basically eliminated the CPUs from doing that. Well, what kind of effect would that have on, say, the latency of system calls in your system? Well, that's something we can use this approach to determine. eBPF, extended Berkeley packet filter, is something that can give us syscall latencies. So we can take all of those, put them into a histogram, look at the 99th percentile of that, and then we can apply the Spectre patch. We can do the same thing, and we can say, hey, our 99th percentile time for system calls has gone from 10 nanoseconds to 30. So that's a pretty big change in performance of your system. And while that's a good initial approach for establishing like a service level objective, like what can I expect my service to return most requests in? What if we could flip that around and say, like, hey, I know that 3 seconds is too long for someone to wait for my service, and I want to know like what percentage of my requests are violating that 3-second service level objective. Well, we can use inverse quantiles to do that. And so an inverse quantile is essentially looking at establishing a value that we want our service to perform at, and then deriving a percentage of requests that have met that criteria. And this is, like I mentioned, this is something that humans are much better at reasoning about. Say if I have a service that, I've got a 10 millisecond service level objective, what percent of my requests are exceeding that? Well, for this data set, 5%. And I can calculate that for one histogram. But like I showed in the heat map previously, what if I want to do that for a month? What if I want to look at how my system changed dynamically? So kind of the reverse of how we calculated quantiles, we can flip that around, reverse the calculations, and get the inverse quantile. So instead of starting with Q, instead we'll start with our sample value X. Say we'll call X 500 milliseconds. We'll walk the histogram until we find that bin, and then we'll use linear interpolation, but we'll reverse it from our previous approach, and we'll solve for our count instead of solving for our value. And I hope you guys like algebra. This may look a little bit daunting, but it's pretty simple. I'll walk through it quickly. My sample value is X on the left-hand side, and I've got my calculation on the right-hand side. This is the same equation I used to calculate the percentile value. So I subtract the left value from X, then I divide by the bin width, then I multiply that times the right count minus the left count, and I add the left count to the other side, and I'm able to isolate Q. I know this might be a little heavy for a slide, but it just shows you, algebra is a good thing to know. So here I've got basically another example of linear interpolation, but instead of having an equation where I try to solve for X, I try to solve for Q, which is the count here. And plugging in the same values from before, I was able to say, okay, if my service level objective is 1.05 seconds, then my value of Q is 700. So, and if I have a total count here of 1,000 samples, I know that I've exceeded my service level objective by 30%. So this kind of flips around the quantile calculations and does the inverse. And I just I added this notation. There's not a lot of official notation out there in literature that I could find, but this essentially gives you the means of calculating how many samples exceeded my service level objective. There's a lot of numbers there and a lot of math, but let's take a look at what does this look like in practice? What kind of visualizations does it give you? So this is a heat map, as I showed previously. It's not resolving too well, but if you look at the vertical line, that's basically representing the histogram overlay at the upper right. So it's a set of histograms over time. Now I can add a set of 99th percentile quantiles. I'm going to turn that up a little bit. But basically, if you see these green lines that fluctuate up and down, you can see that your 99th percentile is varying pretty wildly over this. And this is a year's worth of data. It's about 600 million samples. But as you can see, you've kind of got, I think he might be cutting the lights down a little bit. Okay, give him 1 second. Thank you. That's a little bit better. But you can see, our 99th percentile, for the most part, hovers around 500 milliseconds. But you see these big spikes here every month, and it tops out around 10 seconds, 10,000 milliseconds. And I thought, well, why is that happening? I'm like, well, what happens in network systems around 10 seconds? And I thought, well, there's probably a client timeout going, happening in there somewhere. And this was good, but I said to myself, okay, so I know my 99th percentile is changing, but what if I said, like, I want to know, what percentage of my samples are exceeding, say, 500 milliseconds, because that's when users start to get angry. So I applied an inverse quantile to this, and now we've got a yellow line at the top. On the right side, right y-axis, we have a scale from 0 to 100. So the yellow line basically follows the percent of requests that are meeting our service level objective. So we can see, before I saw like, hey, my 99th percentile went above 10 seconds. Well, how many, what percentage of requests actually violated that? Well, here I can see that when that happens, I've got about 25% of my requests that are exceeding my service level objective. So I thought, well, that's pretty useful. I know the damage is, it's giving me about 25% of damage in terms of SLO, but like what's the absolute damage? Because this might be, in terms of the total number of requests, a percentage is invariant. I might have one request that's not meeting my service level objective, or I might have 1,000. So I went one step further, and I inverted this, and I took that percentage of requests that weren't meeting the service level objective, and I multiplied that times the total number of requests. So now these green spikes here show the total number of requests that are making users angry. And this is an important business metric, because if this is a shopping cart service request during a checkout process, I'm losing a lot of money every time this green line goes up. And I was able to do all that pretty easily just from, there's about, this is about a week, so about 1 million, this is about 6 million data points. So I'm able to figure out exactly how many users I'm making angry, and if I can put a dollar value on that, I can figure out how much money I'm losing. So I can go to the ops guy and say like, hey, when I told you we need all these servers, this is how much money we're losing, so let's go ahead and put a portion of that money to this. But this is still this is just forensic evidence. This doesn't help me when stuff is on fire. So what I can do also is I can calculate, well, give me a graph of the cumulative number of times that I violated my SLO. And we can see that each time the slope of the graph increases, we've got another spike. So that's when stuff is essentially on fire and I'm losing money. And I thought, well, this is good too, but I want to be able to take action on that. And so I took that count of requests that was exceeding the SLO, and I applied an anomaly detection algorithm to it. So this gives me kind of an anomaly score from 0 to 100. It's not machine learning. It's simple statistics space. There's several of them out there in the public domain. So what I can do here is create a threshold alert. Anytime I see an anomaly score of over 60, and page my ops team. So this kind of, this takes. I was able to take kind of the whole circle of, I've got a whole bunch of data, and I can calculate some meaningful statistics from it. But if I, keep pushing that, I can take this all the way to, making these actionable. Because if you look at most telemetry systems that are operating on extremely high volumes of data, they'll say like, hey, our average was, average response time was 5 seconds. But what they don't see is that, that looks fine, but really they're losing these important chunks of data that average is not giving you. This tells you when your system's on fire, tells you when you're losing money. So I was able to, kind of take the whole journey through, hey, what's a histogram? How do we store it? How do we make it fast? How do we store a ton of them? And how can we improve our business with this?